It's not wrong. It's not. Okay, so let's start. Okay, so today we happy to have Zimo from IAS. So he did his undergrad in Peking University, then graduated from Columbia University in 2021, then he did postdoc at Princeton University, and now he's postdoc at IAS. He's gonna teach us how to compute partition functions. Right.
Thanks for the invitation. I talk about partition functions and the associated phase when it's gravity, and the talk will be based on these papers. Okay, we live in a universe with a positive cosmological constant. Unfortunately, we don't have many very powerful theoretical tools, at least not as many as those developed for ADS or flat space. For example, we do not have S matrix in DS. Moreover, we do not have reliable microscopic realization of say DS, the theta spacetime, which is the simplest and most symmetric solution of the Einstein equation with a positive cosmological constant. I'm not sure if everyone is familiar with the theta spacetime, so I'll give a very quick short review. So I think I can see the D plus one dimensional theta. So D is a special dimension, and it's a hypersurface in a D plus two dimensional embedding space, and I take the radius to be 1 for simplicity. And this is a Penrose diagram. Each point in this Penrose diagram is a D minus one dimensional sphere. And this part people usually call it a static patch. It's the causally connected region for an observer here. And the metric is right there. This means the metric on the D minus one dimensional sphere. And T is the time here. This T corresponds to a SO1,1 generator because the isometry group of this spacetime is obviously SO1, D plus 1. So there's no really time translation. And this is a boost, and it acts this way here. So, and if you wiki rotate it, it becomes a sphere. And the sphere is the dominating saddle for the Euclidean action. Of gravity with a positive cosmological constant. Okay, there are various proposals for the CFT, but there are also many problems with them. They are not as concrete as ADS-CFT, and the dictionary is not complete. So given all these limitations, it seems that the best tool we have to study quantum gravity in DS or other similar background is a Euclidean gravitational path integral. And today the talk will focus on Euclidean path integral on the dominating saddle and other subleading saddles for gravity coupled to arbitrary EFT. We will focus on the one loop partition function, and it turns out even such a simple quantity encodes a lot of information that was not known before. Let me start with okay. Let me start with a scalar. T plus 1. Usually we parameterize its mass by delta. We use delta corresponds to the scaling dimension of this operator if you need to see the space time. And if you compute the partition function, log z, say z is just 1 over the functional determinant. It can be written in this way. Q is E2 minus T. And this notation means the dimension of SO D plus 2. This spin n representation of SO D plus 2. And here you can derive it from the heat kernel regularization. Here I express the regulator, UV regulator, or you can treat it it's a dimensional regularization. Why? Because schematically, the T integral gives you something like a log delta plus n and delta bar plus n. That's exactly the eigenvalue. Delta plus n and times delta bar plus n is the eigenvalue of the Laplacian operator. Because this thing has a eigenvalue is n times n plus d, and this is delta bar. So it's just this.
So is this like a Schwinger proper time for?
It's not really time. I use this t, but you shouldn't just, because you can always write. Okay, maybe this is what you meant, right? This t into lambda t. That's something like along that line.
Hmm.
Yeah. Yet this example is very trivial for scalar, but it turns out test structures that persist for spinning field. So if you compute the sum, it's something very simple. I call it chi delta. Here, this function is actually very important. It has a, independent of all the physics here, it has a mathematical meaning. It's called the Harish-Chandra character. Of this group. I mean that, okay, if you consider a scalar field with this mass in the theta space-time, the single particle Hilbert space carries a unitary irreducible representation of the isometric group of SO1, D plus 1. And so you have some Hilbert space, and this quantity can be understood as a chase over the single particle Hilbert space of this thing. So it's purely group theoretical object, but it's not the usual character you've seen, right? For example, in ADS, the character is something like this, and the H is bounded from below, so the sum is well defined. Or if for a compact group, you have the Hilbert space is the finite dimensional, the trace is also well defined. Here, because it's a non-compact group. The Hilbert space is infinite dimensional, and as I mentioned before, H generates the time translation here, but H is a boost operator. It's not bounded, and it has a continuous spectrum. So the trace, or more general, the trace of a group element G only exists as a distribution, and you can, for example, but you can still derive it as a distribution. It has this formula. And more interesting in that this character, if you expand it, it encodes physics in Lorentzian signature. In this sense. It encodes the full polynomial mode spectrum of the scalar field in the theta. So, I'll explain. So these are omega qm, kqn. These are the quasinormal frequency. You have this scalar field in the theta, right? So here I'm doing a Euclidean calculation, but you can also put the same scalar in Lorentzian signature. And you have a scalar field here with mass m, and it has quasinormal modes because there's a horizon. You can impose the influring boundary condition, and you will solve the quasinormal spectrum. And omega qn are the quasinormal frequencies, and this D is the degeneracy or multiplicity of the quasinormal modes. And it turns out that if we can reconstruct this Harish-Chandra character, which I know nothing about the physics here, in this way. And it's a small Q expansion.
Can I just check this? I came in late, so you probably said this. So is chi, it looks like just a sphere partition function of a scalar. Is that right?
This Z is a sphere partition function.
Sorry, is chi the letter partition function?
No, chi is just you can treat it's a mathematically defined object. It's a character for some representation of the group.
Sure.
Yeah. And the partition function is a integral transformation of this character.
Can I think of the partition function as a platistic exponential of your chi?
No, it's not.
You cannot.
It's not.
Okay.
So chi encodes the single particle spectrum.
The single, yeah, so it's
but here it's a multi-particle partition.
Yeah, but that's what platistic exponentials give you.
What?
Platistic exponentials, that's what they give you. They relate the single particle partition.
Yeah, but here then you write it in the. Okay, here it's something. Okay, if you really think about the spectrum of this H, it's the Hamiltonian here. It has a continuous spectrum. But here it really encodes the quasinormal spectrum, not the real spectrum.
Sorry, you're on a sphere, so why is it continuous?
First on sphere you have no Hamiltonian, right?
Okay.
Okay. That H is defined in the Lorentzian picture.
I see.
You have the theta. You have in the static patch. You have time translation, and you have Hamiltonian, which is not bounded, which has continuous spectrum. Yeah, but it connects to the quasinormal modes. And if you really expand it, you find you get something like Q delta plus n. And if you compare this with this definition, it seems that H has eigenvalues delta I times delta plus n, and so you have these imaginary or complex eigenvalues for this Hermitian operator. So that means they are not usually the normal modes. They're not normalizable.
Mm-hmm.
And it looks like two towers. You have two towers. That's actually because the quasinormal modes, they carry two irreducible representations of this algebra, not group, because they are not normalizable. Two lowest weight representation of this algebra. I have to say that for this, there are no lowest weight representation for the unitary. Okay, all the lowest representation for this algebra are non-unitary. All the unitary representation for this group are not lowest weight. And a more physical picture to see the quasinormal modes is you can, so if you push a scalar field to the boundary of ds, this eta is the time, and in the usually we call it in the Poincare patch. So eta goes to 0 at the future boundary. If you push it to the future boundary, you get two operators. Two operators. Okay, it's very similar to ADS. You push it to the z equals 0, you get two primary. And they have scaling dimension delta and delta bar living here. So if we put one, so say one delta here, it can create quasinormal mode in this static patch. It creates the O delta. This primary operator creates the first quasinormal mode with n equals 0. But if you you can see the descendant of this operator, then it creates the n equals 1 quasinormal mode, etc. That's how you see that there are these representation structure, and it's the same for the delta bar. So the picture is that here you compute something off shell in the Euclidean signature, but it encodes something that's physical in the Lorentzian picture, and this picture holds for all the other fields, the spinning fields and the gauge fields.
Maybe there is another marker, but this one is dying. The marker is running out.
Yeah.
Yeah.
Maybe put it in the garbage.
Yeah. Yeah. But
throwing them away.
Next example is a bit less trivial. Is a spin one field? Oh, I think it's a Polchinski field. Maybe I just can't. And with mass m square, the parameterization in this one. That's how you parameterize that mass. And you can do the same calculation, and it turns out, okay. Naively, you just expect something like this. Compared to this one, what's the difference? Here, n labels the spherical harmonics on the sphere. So you expand the field in the spherical harmonics. And here it's a spin one field. You expand in the tensor vector harmonics, and the vector harmonics carry these one box here and n box here carry these representations. So naively, that's what you expect. But it's not correct, because these representations only capture the transverse vectors. If you expand a U1 field a vector field, right? You expand into some in this way. This V mu is transverse. So this so the sum only captures the V mu, but not because it's a massive field. It's not gauge field. It's the phi still contributes, and it's actually to incorporate the phi, there's only a tiny change. You just change this to -1. But theoretically, it's not meaningful, right? Because the n cannot be smaller than 1. But you can, this expression, you can treat it as it can be written in gamma functions, and it's well defined as a gamma function, at least at these numbers, 0 and -1, and it turns out this small change captures the correct potential function.
Sorry, can I check?
Yeah.
Are you saying that you take this part which gets the contributions from the transverse vectors?
Yeah.
You could separately also compute the extra pieces.
Yeah.
And it just the way that they work out after some work,
yeah.
you could recognize that the analytic continuation of this just actually happens.
Yeah.
You have any insight into why the hell that works?
So if you have
What's the intuition?
You have this mass here, right? Mass term here, because this one does not contribute to the f squared part.
I know.
Yeah, and you have and d phi square.
Yes.
You exclude the constant mode.
Yes.
And you get something like if you do the partial integral of phi, you get because each mode gives you 1/m, but you exclude the constant mode.
Yes.
So you get m 1 minus infinity. 1 is the constant mode, and infinity it's a local counter term.
Yeah.
You get m. And it turns out this is 0. Oh, it's 0. And the d minus 1 is 1.
I see.
And then you read off delta minus 1 times delta bar minus 1 after you do the t integral, which correctly captures the mass.
Oh, that's cool.
And it works for all the mass.
Okay, interesting.
And okay, now you can also do the sum. You get almost the same expression. Now the character is slightly different because it's a spin one field, right? The representation is a bit different compared to the scalar. The single particle Hilbert carries a different representation, but actually it's very close to that one. Just this thing multiply the spin degeneracy, and there's an extra term. So this part, it looks like a bulk contribution, right? It's encoded in the quasinormal mode, which is a bulk. Bulk means the static patch here. You can get the same formula if you compute this trace 2 pi h, the multi-particle trace, and but there's an additional piece, which are called edge. Why? Because if you look at if you compare this one with this one, the only difference is d is shifted by 2, d minus 2. So the extra term looks like a path integral on a d minus 1 dimensional sphere.
What about the sign?
Yeah, the sign is also important.
It's like a ghost.
First let me comment. What's the d minus 1 sphere? Why should there be a d minus 1 dimensional sphere? I think the most natural thing is the horizon here. There's a horizon. Okay? For at r equals 1, which is a d minus 1 sphere, and why? Because if you think it's as a thermal partition function, right? And you recreate it from the static patch to sphere, but it's not really the usual thermal partition function, because usually we have it's a product manifold. But here it's not really a product, because here it's a point. It's invariant. It shrinks to a point after you do a weak rotation. So that's related to the edge, and okay, the same structure work for all the spinning field, for photon, graviton, and other spinning fields. You always have this edge structure, and it predicts an infinite data for the edge structure. And very recently, actually, people worked out the edge structure for Maxwell field. They correctly reproduce this contribution. So they classically they show that the whole, if you impose some proper boundary condition, actually they can show that for more general background, as long as there's a horizon, the phase space factorized into a bulk part and a edge part, and they can compute the edge partition function. For example, for the Maxwell case, the edge modes are just the normal electric field, and roughly speaking, they found that for the edge modes, the action is something like this. That's why you have the minus sign here. And I think physically it's because you have some Gauss constraint. And if you have plus also minus sign, if you change the sign here, you lose the locality. You get a log divergence in all the dimensions, which should not be there, which is a requirement of log. Yeah, so this is actually a very interesting result. It gives you a lot of data for the edge modes of the phenom. But for the gravity, the edge modes have not been fully sorted out. But I think people are working on that. If we can produce this result, that would be a very strong evidence for the edge mode. Yeah, I didn't write down this for gravity, but they're the similar structure.
Next basic question. So this is a one partition function for the QFT and K. So
here I only talk about QFT. I have not talked about gravity. Yeah, I talk about gravity. No, I guess.
But can you remind me what is the goal? What are you trying to reach? So there's like a kind of calculation that's very interesting. Where are you heading?
Yeah, the goal is to understand the quantum gravity in when you have a quantum cosmological constant, and because we want to study the Euclidean passage.
So you just reviewed the computation of some field theory partition functions in a fixed background.
Yeah, and also, and now let's okay, extend to gravity. Graviton. Okay. You see the quadratic action of gravity on the fixed the theta background, or in the Euclidean signature on sphere background, and you expect something similar. Okay, the result is similar in the following sense. So for gravity, that it will be okay. First of all, why do we want to do this for gravity? You can of course do the path integral, but it's hard. It's a bit hard because you have this Q gauge degrees freedom and things like that. And actually, people have before this paper, people didn't compute the partition function correctly. I mean, the finite part of that function. Okay, but here the picture is easier because you only need the unshared degrees freedom. You don't need to care those pure gauge degrees freedom. The character, it automatically captures the physical degrees freedom. This because for graviton the scale dimension is 0 and the d. But that's not the full story, because you need to subtract the ghost or the some.
Does the sum really start at -1 now?
Yeah, so it starts at -1. For all spins, it starts from -1.
Are your gravitons massive?
No, it's massless.
But the reason you started at -1 before was because you were dealing with massive degrees of freedom. So what gives?
But it's a bit it's not like more like observation. It always gives the correct result if you start with a -1. But you need to do something extra to get the result, the graviton result.
Right. For you, graviton is just massless spin 2, right?
Yes, massless spin 2.
Yeah. Just maybe let him.
Okay, go on. Yeah. Okay, fine.
Like at least like this expression.
I need 2 here. Yeah, it's some okay. I'll say you treat it as some kind of analytical continuation, like you because you have some delta, right? Delta and the delta bar, which is related to mass, and you analytically continuate to the value corresponding to a massless field, which is D here. And then we do a similar thing for basically for the ghost. We subtract that, and turns out that okay, after some procedure, it gives the correct result. But that's okay. That's probably not the main thing I will do today. But
already, so here I want to ask a question. So that includes gravity now,
yeah, that's included.
right? So gravity is not normalized. So you
Somewhere.
have a cutoff.
Yeah, so it's somewhat like you can do an EFT
So
equation.
what does the cutoff shows in this expression?
Oh, because okay, if you have cutoff, it means you can add the curvature content terms. I have not included in those curvature content. Or do you mean the UV cutoff?
Yeah.
UV cutoff, because I expressed the UV cutoff from the very beginning. Even for scalars, you also have UV cutoff, right? Basically, it cuts off the integral from 0 to infinity. From 0. It's like start from some small number, epsilon, something like that.
I see. So, okay.
Yeah.
So that's not normalized yet?
That's not the wrong idea. I just want to show the structure, but you can always compute it. That's easy thing, right? People know how to compute it.
That's for integrals, like doesn't really start from 0, but you.
Yeah. But okay, in the paper we computed it, but here I just want to show the structure. I don't want to give you those numbers, huge numbers.
Is it linearized gravity on top?
Yes, just the quadratic action of gravity. Yeah. For example, here it's very easy because you know that, for example, in even dimensions you have log divergence, right? The log divergence is actually the 1/t residue of this expression. Yeah, but again, you can also derive the finite part similarly.
But let's say if you cut off the scalar theory at the short distances, there is no particular interactions that you throw away, right? That are super important. But here, the gravity has no terms that going to be like very
but here,
close
okay.
to cutoff.
I didn't include it because here, for example, you have log divergence or other things which is insensitive to the UV physics. It cannot be absorbed by local quantum terms. And also, for example, in all dimensions, all the finite part cannot be absorbed in local quantum terms.
And then what do you do? Then what do you do?
That means those coefficients are physical.
Let me ask you this then. So we have a cutoff at short distances, presumably at Planckian scale, let's say, right?
Yeah.
But you calculating something that is probably dominated by longer distances, is that?
Yes. It's captured only by the Right. So, for example, here in 4D you have the log divergence, and the coefficient is physical. It cannot be removed by the quantum terms. I'm not. Just for the talk, I'm not sure gonna show the details of those expressions, but and because I want to talk about the phase. But in the paper, we indeed discuss all these things. Okay. Here I'm saying show that this is there's something for gravity. You will see something different because we start from n-1. You get some negative powers. It means that the integral will be divergent instead of at the 0, which is regularized by UV cutoff. There are issues at the infinity because of the negative powers of Q. That's actually related to the conformal factor problem. Factor problem of gravity. And then it's also related to the phase I talked about. If you are interested, I can chat about the details later. But let's finish what I planned to say first. So what's the conformal effect problem? So we have that action, Euclidean action. Some I call it kappa. Then if we do a Weyl transformation. And then there'll be a term from this to have a term like this. It means that if sigma with a plus sign, if sigma fluctuates very fast, you can make the Euclidean action arbitrarily negative. And that's the conformal effect problem. And Hawking, I think Hawking, the first one who realized that this conformal factor problem can, it may lead to a complex partition function for gravity. But he realized the problem, but he didn't count the negative modes correctly. The first calculation, the first correct counting is due to Polchinski. Of course, his motivation for studying this partition function of gravity is because of Coleman's work on wormholes and why the cosmological constant should be small. But let me quick review what Polchinski did, and why there's a phase. So okay, now let me just write down the quadratic action on a sphere background. This is the quadratic action. This delta 2 is the second order differential operator. Yeah. Okay. If you want the expression, it would be something like. And the H is the trace of the metric fluctuation. And here I just mean dots just mean I contract one index with the derivative. Okay, this is the quadratic action. It has a diffeomorphism gauge symmetry, and for example, we can the simplest gauge choice here is the Donner gauge, which means that you add this term to the action. You add this term to the action, and then it will remove this term and also the cross term. But it will certainly change this the pure trace part. And then the good thing that in the Donner gauge, the traceless part and the pure trace part of the metric fluctuation, they decouple. And so if I write this way. H bar is a traceless. You plug this in the gauge fixed section. H bar has a positive definite part, but H has a basically wrong sign term. So it's for H you get something like this. This is the action for the action for H. Okay, minus delta square is the Polchinski square is a positive definite operator, but because of this minus sign, most of the modes will be negative definite, except for the L equals 0 and L equals 1 modes. And these are positive, and for L, for the rest, they are negative modes. Because okay, so just calculate because the expression I think is this. This is the eigenvalue of the minus delta square. And okay, for example, in ADS, I think you'll get something like in ADS you get this will be plus. So all the modes will be negative. So you just weak rotate the contour, and then you get a well-defined result. Okay, I think Polchinski did the same thing. He weak rotated the contour here, and then the positive modes become negative, and the negative become positive. So you get a finite number of negative modes, and they say each negative mode picks up a minus I. So you have a one constant mode, and these Lx1 they correspond to conformal Killing vectors that are not Killing vectors. So basically d mu of phi L equals 1. These are conformal Killing vectors on sphere.
So sorry, I'll get lost for that. So that's you started with Euclidean action.
Yeah.
Okay, you're discussing the most, and then you say you do another weak rotation.
No, I'm not. Here it's a weak rotation of the field. Rotate to the contour of the field. Not space time.
Okay.
Yeah, but because before if it's negative, then you weak rotate the contour of H. It goes along the imaginary. Yeah.
You can do that.
Yeah.
Are you taking this expression for the Euclidean action and explaining to us right now how you got the log of the partition function, or what is the order of operations? I got lost. Like what is the connection between your log z and your Euclidean action? Are you getting one from the other?
No. Okay.
No.
The second part.
It's the second part of the talk already.
The talk has two parts. This is the second part started.
The second part started.
It's
It's disjoint.
Yes.
So normally the starting point for getting a partition
No,
function.
really. Here, I observed some divergence,
Right.
some negative power of Q, and I'm saying that it's related to the conformal factor problem. And here I'm explaining the conformal factor problem and how is it related to the negative powers here.
I mean, the reason that I was conjecturing that was that normally to compute the partition function, we start with the action,
Yes.
and then we turn the crank.
Yeah.
So somehow the action appeared after the partition function, which is the opposite of the usual order.
You can do it both ways, and both ways give the same result.
Okay, so the point is to show the consistency.
Yeah.
Now we're
But here
the explanation of this phase.
Yeah, here the goal.
Yes.
Because I don't know. I can talk about this maybe, but I want to also cover the phase.
That's fine. No, I'm looking forward to it. Yes.
Yeah.
It's very good.
Yeah, the two parts. Okay.
It's nice to draw a line.
Draw a line. Yes.
Yeah, so to be clear, what's supposed to be connected to what? Otherwise, it's a little bit.
Okay. Okay. And you have 1 from the constant mode and the d plus 2 from the conformal Killing vector.
Okay, so can you go again? So you write down this differential operator, minus delta squared minus 2 delta.
Yes.
Okay, so then what's on the next line?
Okay, maybe I should write it here so you can see.
Well, yeah, I can see that I forgot what's L.
Okay. L are the angular momentum. Okay, I just okay. So you have this is the action, right? After you rotated the contour of the field. L. So this thing, the operator has eigenvalues L times L plus D, and L are labeled spherical harmonics on the sphere. Because now H is like a scalar field, right? So it can be expanded in the spherical harmonic into spherical harmonics on the sphere. And I'm saying that after you do this, there are some negative modes, which is the constant mode and the L equals 1 modes, which are conformal Killing vectors. And you have which gives according to Polchinski, you get minus I for each negative mode. So you get 1 from the constant mode, and the Lx1 mode, there are d plus 2 of them. just a spin-1 representation of SOD plus 2.
Just the face in the passing.
Yeah, so he got the phase in this phase in passing for gravity. And this basically this destroys Coleman's proposal for the why this interpretation why the constant should be small. But actually there are some subtleties here that we discovered in this paper with Zimo Sun and his students, and the reason is following. Okay, if okay, this is the result if you weak rotate the contour. Let's say if we don't.
Just remind us, the proposal you mentioned is like the peaking of the wave function at the small lambda, or what kind of proposal by Coleman?
Oh, Coleman's proposal is, I think he said it's a sum of spheres, and I think it's a partition function. He sum of spheres, and you get something like this.
One over lambda.
Something like this, and you want the lambda to be small. But if S is imaginary, then just does not work.
Can I check? So to get this, you analytically continue the field space.
Yeah.
And,
For the trace part.
right, and you got some factors of I as a result.
Yes. Yes.
So when we allow complexified paths in the path integral,
Yes.
we have to watch out for Stokes constants,
Yes.
Stokes multipliers.
Yes.
How do you know what they are? How do you know you can take that phase seriously at face value?
Yeah, that's something so it's we just take okay, we say we for example we can complexify G Newton a little bit, give it a small phase, small I epsilon, and then you can determine where you rotate the contour.
But that can be a Stokes multiplier. I mean,
Violent things can happen to rotate 90
yeah, exactly,
Yeah.
exactly. That's the point. There can be Stokes phenomena.
So, yeah.
So, and then there can be extra factors of I coming from that. I mean, how do you know that there aren't? I mean, you're doing something that's a little bit. Yeah, I mean, I like that kind of thing, but it's tricky.
There are people arguing this probably the Euclidean passing just is not well defined. Some people say you should do a Lorentzian path integral, but okay, this is what we can do even this.
Okay.
Even that.
So you just like, I mean, that's also fine. So you do it and believe that it works.
Yeah. That's it. That's the idea. Yeah. Then probably it's related to what you said. So if we do a different way, if we don't weak rotate the contour, we still have.
Sorry, I had another question. So, like, you say that the fact that we have this phase like kills this whole argument. Is like the partition function just a pure phase?
Yeah, it's a partition function is a. So you have the partition function is e to the this is a tree level partition function, but tree level action, right?
Mm.
And then you have the one loop part. You multiply the one loop part, and the one loop part has some I.
Okay.
So Z is something like this.
Okay.
And then you.
So the one loop part is like pure.
Oh, sorry. This Z is a different Z. Sorry, that's you sum up spheres. This is for a single sphere, and he said you need sum up spheres.
In field theory, when that kind of thing happens, quite often the resolution is either you missed the Stokes multiplier, or, well, relatedly, the Stokes multiplier could have been I itself, or the Stokes multiplier is 0, and this thing doesn't contribute at all. So so basically this doesn't feel like enough, you're kind of stopping at the most, you seem like you're saying something that needs an extra step to actually make it convincing.
Yeah, that's what we talked about the other actually different counting that give you the different phase.
Okay.
So if we don't weak rotate the contour.
So that result is like dependent on the procedure.
Yes, that's what we want.
Oh.
So but that's even more disturbing.
But that's that's very bad. Right.
That's what we noticed that. Okay, so this is what you do.
Yes.
This is what the Polchinski do. He weak rotate the contour and put the plug. It becomes plus. I say we don't weak rotate the contour.
Okay.
And and you have most of the spectrum is negative definite. except d plus 3 of them. Some low-lying modes are still positive for this section. And then if you say I absorb the local quantum, I get I to d plus 3 instead of minus I to d plus 3.
How do you know that's the right finite part?
Yeah.
Again?
Yeah, I mean, how do you know there's no finite part? Changes the story.
Yeah.
You're manipulating infinities pretty cavalierly in this argument.
What do you mean by the finite part?
Well,
I mean, you're throwing away an infinite thing. There's
Yeah.
typically, there can be a finite part left over. How do you know what it is? How do you fix the finite part?
Do you mean a finite counter term you can add?
Yeah, how do you know that this answer doesn't depend on the finite counter?
Yeah, you can add the finite count terms, but you don't want them to have a imaginary or complex coefficient because that will give you a complex Hamiltonian in the Lorentz picture.
but still you need to, so you want to somehow subtract this infinity.
Yes.
So.
But that's sort of like the infinity you subtract. I show the mass, right? You have this.
What?
Before the passing integral, I have this mass, right?
Mass of what? So
for the massive U1 field, I discard the same infinity, if you remember. For the longitudinal part of the A mu. Remember, the passing integral give you something like 1 over m, and I write it as something like this.
I missed that.
Yeah. Yeah, sorry.
Well, I should have asked the question then.
Well,
I mean, you know.
But then anyway, there's no I in there. But anyway, there's no I in there, but there's an I here.
But I mean,
So
it's the same type of divergence.
So this is probably getting too technical. Like, can I just ask, like, in the paper, did you guys write expressions that didn't just involve naive manipulations of infinity? Is there like a concrete expression just in the paper? Because you just say we did it carefully, and that's
you can do it using each kernel. It's the same thing.
You still have to fix the finite parts, but okay, I'm going to trust that you did it right. It's fine. Fine.
The finite part. Okay, what do you mean by the finite? The finite part, you mean you can add finite counter terms.
Yeah.
Is that what I'm saying?
Yeah.
Yeah.
You can do whatever you want with them, as long as you maintain some conditions. But
yeah, okay. Polchinski's ideas, yes, you can add some curvature counter terms like R wedge R or something.
Yeah. All kinds of fun stuff. Yeah.
But okay, for example, if you want a parity invariance, you drop this one.
Yes.
But then he said, okay, because we don't want a complex Hamiltonian. Then he said we only drop the infinite. Only the infinite quantum is allowed to be complex. But yeah, but if you're allowed to add,
sounds a little dodgy, to be honest. But okay, fine.
If you allow any finite curvature quantum, yes, then it can be anything.
I mean, okay.
But you can say the same thing in all dimensions, right? Then you cannot add something like that.
Yeah. No, I'm not saying it's impossible to get it right. I'm just saying that, like, once.
Yes,
It's an obvious. So I hope it's an obvious reality. Like you can see why it raises questions when you write expressions with infinities and just like say like okay, like okay, it's okay. It's okay.
And okay, there are two ways.
Yeah.
We're trying to say that this is the better way because it's a gauge invariant result in the following sense. Here you pick the down the gauge, but you can choose any arbitrary gauge. And if you choose other gauge and let me show the details. So you can choose the arbitrary gauge, then the trace part and the traceless part do not decouple. So we need to do a more sophisticated field decomposition. We need to do something like this. This is a transpose traceless, and this. This is orthogonal to the Killing vectors. And I call it chi maybe. trace mark, like this. And this thing should be orthogonal to L equals 0 and L equals 1. L equals is annihilated by the differential operators, and L equals 1, they are, as I mentioned, they are Killing vectors, they are conformal Killing vectors, and they can be written in this form. So to make the decomposition unique, chi has to be orthogonal to these modes. And okay, after some okay, there's also a bit field redefinition, but that's something like this. So you get chi is mostly positive. So mostly negative. And there are n of them at negative mode, and minus plus 3, because they are also to this mode. Okay, if we follow Polchinski's procedure, I recruited these 5 fields because most of the spectrum is negative definite. I'll get minus, 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 minus here. So in the end, if I follow this procedure, Polchinski's procedure, get n minus d plus 3 plus n. So there'll be a minus 2n power. But if you do this thing, it'll be different. If I don't weak rotate the contour, the field contour here, the phi contribution would be minus I infinity minus n plus 3. And there I get minus I, sorry, minus n. That's plus 3. So the n dependence just drops out. They cancel. If you follow this counting procedure, the result is independent of, because this n can depend on the gauge fixing you choose. You can add some, you can change this to some different numbers, and you get different n. And okay, so and also, okay, what time is it?
It's like 1:29.
Okay. And Maussan had this proposal that if you include an observer in this picture, and it can get rid of, you can change this to IQ. Basically, treat the observer as a massive particle on a sphere, and some of the conformal Killing vectors will move the observer. So those should be, roughly speaking, those should be removed. And then you also need to introduce you also need to impose the Hamiltonian constraint for the combined system of the theta and the observer. And roughly speaking, you get a 1 for that Partition function. And then he also conjectured that a better model for observer is a black hole in DS, which means that if that's true, it means that if we compute the Partition function in the black hole background, it should have this I₂ phase, the same as the theta plus massive particle as a observer. And then we did the calculation for a charged black hole in DS. I draw the loud region QM. It has this shock thing. So the region inside is a loud region, but not every Q and M, not every pair of Q and M gives a smooth Euclidean geometry, or in other words, it's more. equilibrium. So there are only two lines that meets Euclidean geometry. This is what we call the lukewarm, and this is Narii. And we found that here for Narii there's no phase, and here, but for this region, it's still allowed. If the charge of Narii is big enough, it'll be I cube. And the reason is that the three negative modes will become positive if you crank up the charge. And it implies that there should be also the I cube from this branch, and then it's later tested or verified by the Stanford group. They do a S-wave approximation for this problem. So basically, you have the theta 2 times S. You have a charged black hole in 4D. So it's charged. It's magnetically charged on a 2 sphere, and they can see the S wave only S wave on the sphere. So they reduce it to a 2D gravity problem, and then you numerically solve the spectrum of the system, and they found the I cube here. So it's consistent with this conjecture here. So it seems that the black hole is indeed a good model for observer. And okay, to wrap up, I just want to mention that the phase actually exists for all the massless high spin fields, and you can compute we can compute the phase as if we think about the Vasiljev theory, we have the infinite tower of massless high spin fields, and we found that, say, in dimensional organization, if we sum up the phase, it becomes 0. And a natural question we want to understand is that related to the observer, or just the high spin gravity is bad? It has maybe has a dual. Yeah. Okay.
Well, returning to this Coleman proposal that you mentioned, like, is any particular lesson that we should take for it? Because Polchinski, as you said, was reacting to the proposal that I don't know how it's called, wave function of the universe is sharply peaked at going to 0, right? And so he found the complexity that makes this, I guess, problematic, right? And your result is doing what exactly?
Here, first we found that there are two ways to consider it,
okay.
And this one is consistent with the gauge invariance.
Yeah, but now if you apply it to Coleman's argument,
yeah, it's still the same thing.
Still there is,
but now it seems in this paper we seem to, if you add up you have the high spin theory, it seems, or you have some other theory where you can cancel the phase, then maybe the Coleman's proposal can still work. But it seems hard to cancel the phase, and now we find that only this high spin field has phase, but to have a consistent theory, you have to include all of them.
Another question?
Just a quick question. Can you reproduce those partition functions from the equation? I saw us like AAS can do something to match those.
I'm not well if anyone did that.
If not, let's send speaker again. We will have a speaker dinner, probably leaving at 5:30. So please let me know reactions like if you want to join.
What wait. You mean Euclidean ADS partition function? But they also did people also just did the Euclidean calculation.
This department is very fortunate to have you, right?
Yeah.
It's just here.
And I was wondering,